Hello, my name is Darren Key, and welcome to the fourth webinar in this series by Optimized Thermal Systems. This webinar is called Optimization, Cost, and Health Benefits of Copper Tube Plate Fin Heat Exchangers. Once again, my name is Darren. I am with Optimized Thermal Systems, and I'll be presenting the material today along with Yoram Shabty of Heat Transfer Technologies. Yoram will be presenting the cost model, and I'll be presenting the other portions of the presentation. Just a brief overview of the contents here. There'll be an introduction. We'll go over the fundamentals of small diameter tube fin heat exchangers, discuss the benefits of copper, specifically looking at the health benefits and the antimicrobial properties and reduced fouling of using copper. I'll discuss the evolution of copper tube fin heat exchangers and the benefits of smaller tubes. And then we'll get into the meat of it, where we'll take a look at the recent research for 5mm and 3mm heat exchangers and some of the case studies, some success stories that we've had there. And I'll hand it over to Yoram for the cost model and then conclusions and takeaways. So the introduction. So as I said, this will be the fourth webinar in the series. The previous three are listed here. A lot of the material that I'll be presenting today is similar to what was presented in webinar 1, advantages of small diameter copper tube fin heat exchangers. There's a lot of great material there about the physics and thermodynamics of going to a small diameter tube, so I highly encourage that you take a look at that. The second webinar is great for general principles on how tube fin heat exchangers are produced. And then the third webinar is effectively designing smaller tube fin heat exchangers and specifically taking a look at Coil Designer, which is a software produced by Optimized Thermal Systems. And then later on this year, we'll be releasing 2 more webinars where we take a look at designing heat exchangers specifically for alternative refrigerants. So there's a lot of new refrigerants coming online, low GWP refrigerants, things like that. So things to consider when designing for that. And then also the impacts of frost development on heat exchangers, specifically with respect to small diameter heat exchangers. So if you made it this far, presumably you know what a tube fin heat exchanger is, but just to have it on record, so copper tubes, refrigerant flows through the tubes. Those tubes are connected to each other with U-bends, and then we use fins, which are touching the tubes, to effectively extend the heat transfer surface area. So that's the meat and potatoes of it. Typically, common construction would be copper tubes with aluminum fins, although there's certainly many other combinations that are common in industry. And then shown down here, we'll see this picture again later. This is copper tubes and copper fins, and depending on your application, it might make sense to do such a thing. So what's our motivation here? What drives heat exchanger design? Again, this is a slide from that previous webinar 1, but just in general, we want energy efficiency to go up. We want environment and safety to go up, and we want cost to go down. So everything that I'll be presenting here today is keeping these 3 main parameters in mind. So let's discuss some of the inherent benefits of copper. So for copper tubes, copper has high thermal conductivity, which leads to a low wall thermal resistance, so better overall heat transfer. Copper has a heat transfer coefficient of 380 watts per meter Kelvin, as opposed to aluminum, which is a bit lower, and stainless steel even lower still. Copper also has natural corrosion and biofouling resistance and antimicrobial properties. This helps protect the copper from degradation. I'll clean that up. Copper is compatible with pretty much all refrigerants used today except for ammonia, so very versatile material, and it is soft and pliable, which is helpful for applying inner grooving or enhancements to the inside of the tubes, which can help increase heat transfer. Now the topic of this particular webinar, smaller diameter. The benefits of smaller diameter is that we end up with thinner walls and can have less charge. So the thinner wall leads to lower thermal resistance of the system, of the copper tube, and that smaller overall diameter results in lower hoop stresses, and the tube can actually withstand higher pressures. So like when designing for like a CO2 system, for example, we can end up withstanding a lot higher pressures. So I think there are some copper alloys out there that can withstand up to 120 bar, so pretty high pressure for those small tubes. And then finally, obviously, smaller tubes, there's less material and less material cost. That's a big one that we will see when Yoram does his cost model. Copper fins, I'll probably end up taking this out. So let's dig a bit more into the antimicrobial benefits of copper. So one of the things that's become increasingly more important, especially in the eyes of the general public, it's typically pretty important for HVAC designers, but during the coronavirus pandemic, is indoor air quality. And copper has been shown to suppress the growth of bacteria and molds that can be present on a surface. So I want to be clear that I'm not making claims that copper heat exchangers can protect you from coronavirus. That's far beyond my area of expertise. But copper has indeed been shown to suppress the growth of molds and bacteria and some viruses, including SARS-CoV-2, which is actually the virus responsible for coronavirus. Copper does have an EPA registration. It's a treated article exemption, which allows HVAC manufacturers to make product protection claims that by suppressing the growth of bacteria and molds that can reduce system efficiency and cause product deterioration or foul odors. And this treated article exemption actually applies to a very wide range of equipment ductwork. You can check up the EPA registration here. Just take a look at that. And it applies to heat exchangers, ductwork, drip pans, a wide variety of HVAC equipment. So let's take a look at a couple of case studies. The first will be the Fort Jackson, South Carolina barracks study. Sorry, this is case studies for the antimicrobial effects of copper. So copper heat exchangers. So in this study, in identical barracks, nearly identical barracks, the heat exchangers and drip pans were replaced in both barracks. In one, they were replaced with copper assembly, and in the other, with an aluminum assembly. Then, over the course of the study, there were air samples taken of outdoor air, vent air, and then room air during both heating and cooling season. Couple things. As expected, having an HVAC, couple things to note. The CFU, which is a colony forming unit, is higher during the cooling season, and this is to be expected as during cooling season there's condensation on the coils and promotes the growth of fungus and bacteria. During heating season, there was the aluminum heat exchanger had a CFU 2.1 times higher in the room and 2.4 in the vent. So, that is to be expected, that the vent might be worse than what's in the actual room. And then during cooling season, the aluminum had a 3.1 times higher in both the vent room and the vent. So we see here that the copper heat exchangers were found to reduce airborne and fungal concentrations in the room in a statistically significant degree. Definitely need to practice saying that. The next biofouling study was done at a New England middle school. This was a pretty interesting study. They replaced a heat exchanger with an all copper unit. So that's the frame, the tubes, the fins, everything was copper. That's what's shown here. It's a really, really beautiful example in my opinion. This study looked at 3 identical air handling units. The first one used the existing copper tube and aluminum fin heat exchanger with UV lights. So UV lights are commonly used to suppress biofouling on coils. Air handling unit number 5, that was the second one in the study, had no UV lights and 100% copper or copper alloy, copper tube and copper fin coils. And then air handling unit number 6 had also no UV lights, but just the original copper tube and aluminum fin coils. The results of this showed that biogrowth was successfully controlled by copper tube and copper fin coils, even without the use of the UV GI light. So takeaways from antimicrobial effects. Copper does successfully suppress the fouling of coils without the use of UV-GI. Copper heat exchangers can significantly reduce airborne fungal concentrations when compared especially with aluminum assemblies, and thus improving indoor air quality. Potential benefits include reduced energy consumption due to that might result from anti-fouling and maximization of airflow. There can be reduced energy consumption from the elimination of UV-GI equipment, so you just don't have to have that extra piece of equipment. You also don't have to maintain the coils or clean the coils quite as often, and you don't have to maintain that UV-GI equipment either. Couple things that we recommend looking into would be energy efficiency losses due to coil fouling or reduced airflow, economic impacts of copper tube, copper fin heat exchangers. So it's probably that tipping point somewhere where it does make more sense to invest in that copper tube, copper fin heat exchanger, and then also looking at a little bit more closely the indoor air quality. Now, a brief recap of the evolution of copper tube fin heat exchangers. Again, this is coming from the webinar 1. There's a lot of information in there, so definitely recommend you go back and take a look at that. There's a lot of information on this slide, but what I want you to focus on is on the x-axis we have tube diameter, so that's the outer diameter of the tube, and then the air side surface density, so that's the heat transfer surface area of the heat exchanger versus the total volume or total envelope of that heat exchanger. So as we move from right to left, we see that the internal volume of the heat exchanger goes down and the air side surface density goes steadily up. So one thing, if we use, for example, a 7mm tube as our baseline, we're able to go to a 5mm tube. There's actually a 56% reduction in internal volume going from that 7 to the 5mm tube. And then if we go even further to the 3mm tube, there's actually an 89% reduction in internal volume of that tube. So the reason this is significant is, as the standard of evaluation moves towards overall global warming impact of an air conditioning unit, or really any system, we're going to be looking at that rather than just energy use. So, For example, if you're using R410A as your refrigerant, that has a global warming potential of over 2,000, so any reduction in heat exchanger internal volume has a resultant reduction in that charge required for that system, and then a reduction in the global warming potential of that system. So we'll get into more of that in webinar 5. So main takeaways of moving to a smaller diameter tube. You have a more compact surface, so you have more heat transfer surface per volume or per envelope of your heat exchanger. It's less material required in that system, in that heat exchanger. That feeds into the cost model nicely. There's also smaller internal volume, which means less refrigerant charge. And there's increased hoop stresses, improved hoop stresses, which allows for higher operating pressures, which plays in nicely with the transition to some of these new refrigerants. One thing to keep in mind is that as hydraulic diameter goes down, heat transfer coefficient goes up, which is good, but friction factor also goes up, which is not good. So only reason I draw your attention to that is that you can't just expect to change to smaller tubes and expect the system to perform better overall. You have to redesign your heat exchanger in an intelligent way, and OTS has software tools to help you do that. And I'll probably delete these. These are discussed in the previous webinar. Take a look there. So I've been teasing this a few times. This is Coil Designer, which is produced by OTS. It's highly customizable for whatever your needs might be for your particular application. And yeah, you can take a look at webinar 3 on the website for more details on what the capabilities of this system is. But one thing that's changed since that webinar is that Coil Designer now includes a range of correlations for tubes less than 5 millimeters, which is a lot of the heat exchanger tools out there don't have that capability. So that's a space that you're looking to get into. Check us out at optimizedthermalsystems.com and you can request a free trial. Now let's take a look at some case studies of 5 and 3 millimeter heat exchangers. So we're going to take a look at 2 case studies. The first one was a water heater study in which OTS was asked to come up with a heat exchanger design to replace a 5/16 inch or approximately 8 millimeter tube evaporator for a residential heat pump water heater. And they wanted to replace that with something in the 5 millimeter tube range. So that's case 1 down here. So this is kind of a bread and butter reduction in tube size case study. So there's a existing state-of-the-art heat exchanger, and for whatever reason, either they want more capacity or reduction in material or whatever it might be, and can achieve all those with a smaller diameter tube heat exchanger. So that'll be case 1, and then we'll also take a look at case 2, in which HVAC OEM wanted to replace microchannel condensers with something in the 3 to 5 millimeter tube range. So the reason we're going to do this case study is this is kind of going in the opposite direction as what would be more typical, I guess. So going from a microchannel heat exchanger to a larger diameter, but still in the small 3 to 5 millimeter range. The reason we're doing this one is to show that microchannel heat exchangers have a lot of promise, and as time goes on, that's probably going to be really great technology. But this still is considered cutting edge, and maybe the manufacturing techniques aren't quite there yet, or the design isn't quite there yet. But capital expense to produce those in-house might not quite be there yet, so that's why we're doing case 2. So case 1, the heat pump water heater. So the goal here was to increase evaporator capacity of a residential heat pump water heater. So the evaporator size will be limited by the equipment enclosure, so they don't want to change the equipment enclosure at all. They want this to be as close to a drop-in replacement as possible. The existing coil, as I said, is about 8 millimeters with copper tubes and aluminum louvered fins. And the goal here is to increase heat load capacity and minimize fan power. So designing to those 2 parameters and inputting a whole host of other parameters as specified by the client. This is a sort of a typical output of what you might get from our design tools. So, oops, what happened? Here we go. So on the x-axis, we have normalized heat load. On the y-axis, we have normalized fan pumping power. The baseline design, which was the original design, is here at 1,1, right here. And then we increased fan power and saw what the resultant capacity was as a result. So this first curve that you see here, this is just the original heat exchanger with increasingly higher fan pumping power. And of course, if you turn the fan up, you can get more capacity there. With the optimization tools, we optimized a 2-row design, 3-row design, and a 4-row design. And OTS took a closer look at 3 of those hundreds of designs that were generated, design 1, 2, and 3. Each of those represent the optimized design for those particular parameters. So this first one was selected. It has the same fan pumping power. That's design 1, and it has approximately 30% better performance. The design 2 was selected because it's at 2x the fan pumping power. That has about 50% more capacity. And then just to see kind of not quite the upper limit, but perhaps effectively an upper limit of what the system might be able to produce capacity-wise, that's where design 3 is. The customer, in fact, decided to build and test this design 1, which had, I believe, that's in the 3-row range. For the sake of the cost model, since this is, like I said, kind of a bread and butter example, for the sake of the cost model, we took a look at the material required for this, and we're calling design 0 here. So that was selected because it has the same fan pumping power, but has a little bit higher capacity, I think about 16% higher capacity than the baseline. So again, design 0 will come into play during Yorum's cost model. So here's just a bunch of numbers that show the improvement of the design. And again, the goal here was maximizing heat load capacity while minimizing fan pumping power. So like I said, the client decided to actually build and test this particular design. So 32% capacity increase, no change in fan pumping power, which is what they wanted. Yep, that's what they're going to do moving forward. So the next case study is for the HVAC OEM, in which they wanted to replace a microchannel heat exchanger for a heat pump condenser with something that they could build in-house, which would be in the 3 to 5 millimeter tube range. So the microchannel heat exchanger was actually purchased from a third-party supplier. They wanted to bring that back in-house. And this was actually for 2 separate systems. One was a residential system, which was a 2-ton system, The other was a commercial 10-ton system. So again, the constraints here had to be drop-in replacement. So same envelope, height, width, and depth, similar fin density, refrigerant pressure drop, and refrigerant charge. Those are all inputs into the optimization tools. And the goal here is to optimize heat load and minimize airside pressure drop. So here's a similar output as to what you saw before. On the x-axis, we have normalized airside pressure drop, and on the y-axis, normalized heat load. This green box here shows all the designs. Anything in this green box dominates the baseline. Here's the baseline here at 1.1. Anything in the green box dominates the baseline, both in terms of pressure drop and heat load. This was actually a two-part study. The first part of the study, the client wanted to see what the maximum capability would be of a smaller diameter, a 5mm tube heat exchanger with off-the-shelf fin designs. So this batch here, these three right here, was wavy off-the-shelf fin designs, and then using wavy off-the-shelf fin designs, and then this is using louvered off-the-shelf fin designs. And as you can see, the heat load, the range in the heat load on the y-axis is pretty small. So heat capacity wise, these off-the-shelf fin designs are pretty close to that microchannel heat exchanger. Not quite as good, but pretty darn close. There's a little bit of a penalty on the airside pressure drop, but depending on how they're actually going to be using the system, this may or may not be acceptable to them. The second phase of this study was to come up with a optimized but still manufacturable fin design. So input all of the parameters required for a manufacturable fin, let the software do its thing, and that's all these other squares and I guess those are ovals, squares and ovals. So lots of good options there. And then I've highlighted once again one of these designs here, and that will be discussed further in Yoram's cost model. This is the very similar setup, but in this case for the residential design. The main takeaway here is, again, we see off-the-shelf fin designs performing quite well. In fact, note the range here for the heat load is even smaller than it was before. So the off-the-shelf fin designs work quite well with an optimized tube and circuitry. And then there are some optimized tube and fin designs that actually dominate the baseline here, which is at 1.1. So takeaways here are that an optimized 5mm design can be competitive against a 2-ton and 10-ton microchannel heat exchanger. So that's in terms of airside pressure drop, heat load, coefficient of performance, face area, mass, volume, taking all these things into consideration. Still possible to come up with a 5mm design that competes with the microchannel heat exchanger. There's too many numbers here. I'll delete most of those. And then if we take it one step farther and optimize the fins as well as the tubes, we can come up with something where the system can outperform slightly, but still outperform the microchannel heat exchanger for both the larger 10-ton commercial and 2-ton residential with respect to heat load and airside pressure drop. Now I'll hand it off to Yoram for the cost model. Yoram will discuss these slides. And just a little teaser, thank you Yoram for the cost model. Just a little teaser for what's to come next. Webinar 5 will be in a couple months. We'll take a look at, I'll alternative refrigerants and what that means for smaller tube fin heat exchangers. So there's a bunch of alternative refrigerants currently under consideration, mostly for environmental reasons, other reasons as well. And we want to take a look at how a copper tube fin heat exchanger design needs to change for these various new refrigerants. Webinar 6 should be really interesting. I'm excited for that one. We'll be taking a look at the impacts of frost as your heat exchanger tubes get smaller and smaller. Another technique is that fin density gets tighter and makes it more susceptible to buildup of frost. So we'll be discussing potential performance degradation from water bridging and frost and possible mitigations. Thank you very much, and here's our contact information.